And we were getting creative and cutting styrofoam to look like rocks and everything. I was doing great, man. You know, 3 hours into it, all these rocks. Okay, and then, whoosh, dang it. I almost made it all night. Sliced it pretty good. All right. So there's my Valentine to you guys. I picked this one. You can read on the right, that's Galileo, the good experimentalist. I like him because he did demos. A lot of people, remember, debated. Oh, it's this, it's this. Well, you know what? Do an experiment. Let's see what happens. And he did. So, and this is the one I like where, remember, you stand on a bathroom scale and it reads your weight. But Newton's third law says all forces come in pairs. And most people think, oh, well, if you push on the scale, it pushes back on you. But what's causing you to move down in the first place? Yeah, the earth pulling on you, gravity. So the earth pulls on you, so you pull on the earth. That's the reaction of that force. So, you know, the earth moves whenever we're together. Or remember that if you have your sweetheart tonight or something. Just the fact that you each have matter, you're made up of mass, you gravitationally attract each other, whether you do physically or not. So. And the force is mutual, right? Whatever attraction I have for you is reciprocated gravitationally. So. All right. Got an animation for you. Where's that? It's in Firefox. So we have a few things to finish up with relativity, and then the remainder of the time we'll review the other stuff. So this is a simple animation, but just to drive it home, because we haven't talked about length contraction as much as the time. So if you have a spaceship at the top, and its length is 10 meters, and then you have a spaceship at the bottom, and its speed, you can see there at the bottom right here, there's a slider, and I can adjust its speed. So it's going slow now, non-relativistic. It's kind of a crude borderline. Well, when do you have to start worrying about relativity? Because remember, Newton's laws work in slow speeds, what we're used to. Relativity works at high speeds. Does relativity work at low speeds?
Not as much.
Absolutely. They have to agree. That's that correspondence principle I just touched on at the end of last time. Well, sure, any new theory has to agree with the old ones that are correct. So yeah, it's like relativity is more general. It works for all speeds. It's just at slow speeds, it reduces to something simpler, everything we've already covered with Newton. So yeah, Newton only works at slow. It breaks down when you start going fast. So it's kind of like an approximation at slow speeds. Works just great. But relativity works at all speeds. It's just why make it complicated when you're going really slow? You don't have to.
Is that why they don't throw out Newton and just use relativity?
Right, because Newton's laws are right for slow speeds. But when you start dealing with particle accelerators and satellites whizzing around the Earth, you're getting closer to the speed of light, and these differences show up. So yeah, now you need to start using relativity to be accurate. Hence, GPS systems need to use relativity, or they're too far off. So that works for length differences, time differences, momentum, energy. All those are changed or affected, adjusted, if you will, at higher speeds. But all of those work at the slow speeds. Okay. So here you can see that the bottom one going a tenth of the speed of light, down here, tenth the speed of light, that it's contracted. If you were to view that passing spaceship, it would look like it's only 9.95 meters long. That would be your measurement. It's not just a perception thing. That's what you'd measure. It would look that short to you. What if you're riding in the moving spaceship? What would you measure its length to be? Good, 10, because you're at rest with respect to the moving ship. You're with it. So you don't get any difference there. You only see differences in the other frame, whether you're moving or not. You know what I mean? So if you're at rest in the top ship, the upper ship, the bottom ship's moving relative to you, so you see it contracted. And its time slowed down. If you're in the bottom moving ship and you're looking at the top ship at rest, say it's perfectly at rest, what do you notice? You're in the bottom moving ship, but you're observing the ship at rest. What do you observe? Why is it still smaller?
Technically, if you're in the ship, you could say that you're at rest and they're moving.
That's right. That's my point. Motion's relative. If thinking there's no windows or whatever, you can't tell who's the one really moving, but there's motion between you. It's relative, right? So whether you're moving or they're moving, it's like the other guy is moving, right? And so you perceive a difference for the other frame. Again, your frame, things seem normal. The other guy's frame seems normal to them. But when I look at him, huh? And when he looks at her, huh? That's when you get differences. Does that make sense? So let's speed it up. This accurately plugs in the numbers of that equation with the Lorentz factor. So if we go a little faster, let's just jump up to half the speed of light here. So it accelerates up to that speed, becomes a uniformly moving reference frame. It's now at a constant velocity of half the speed of light. And you can see, us at rest observing it, it looks shorter. Only in the direction it's moving, though. Direction of motion. Notice it didn't get shorter top to bottom, because it's moving sideways to us, so that's the way the length gets contracted. You follow me there? You only get contraction in the direction of motion. But likewise, now we hop in the moving ship and look back at the ship at rest, it would look contracted the same amount when you're observing the other guy. And let's go 90% the speed of light, and you get the idea. It really seems squashed. That's what you'd measure, observing it. Yeah?
Could you talk about the time dilation factor here as well?
So it's the same factor, because if space contracts a certain amount, here, let's pick one here. I memorize one. Your author likes to use it at, whoop, come on. One more there. At 87% the speed of light, the Lorentz factor is 2. That's why I memorized that one, because it's convenient. So at 87% speed of light, the Lorentz factor is 2. So that ship is half the length. Here, I can even pause it. Let's see. Close enough. And so if the space is cut in half, time has to be adjusted by the same factor. And so if you were observing the other guy, his time would seem to run twice as slowly. Things would take twice the time.
So could you talk about that from the aging point of view, about how a guy in the bottom frame would age slower?
Yes, let's do that. That's time dilation in the twin trip. So I have a video that I'm going to play for that. When we get to it, it's a little hokey, but oh, I forgot an audio cable. 20 seconds. Okay, so the gist here is the twin trip thing. I use you guys, so we'll do it again. Let's say you're twins, right? That's believable.
Oh, yeah.
Just so that you're the same age. Who wants to go on the ride?
I do.
Okay, we send her off in a spaceship near the speed of light. She travels. Okay, while she's traveling at a constant speed, what do we notice about her? What's going to seem different to us about her? The length's going to contract and her time slows down. All time, even the biological clock. So she appears to be aging more slowly than us. Okay, now we're on the ship with her. What do we notice about the twin at home? At this point, we just see, is she moving relative to us?
Yes.
We think we're at rest. So she's moving relative to us. So it'd be the same observation. We see her length is contracted and her time running more slowly. This is why sometimes it's called the twin paradox. Because wait, they both think the other one's younger. Aging more slowly. Huh? They're both right. That's why relativity is a little weird. Okay, now she wants to come back home. So she has to decelerate, stop, turn around, accelerate back up, and now she's back at, say, the same speed, constant speed coming back. While she's coming back, what does she observe about the twin at home? Yeah, she still looks like she's aging more slowly because she's in motion relative to us. And the twin at home observes her coming back, same observation. She looks younger. So they're still apparently disagreeing. The weird part is, okay, they come back together on Earth. They're all at rest with respect to each other. Who's the one that's really younger? Or are they back to the same age magically?
The one in space is younger.
You say the one in space is younger? Would they both agree on that?
Yeah.
Okay, any other votes? No other votes? Who's confused? Doesn't know which way to vote. Yeah, that's only a few of you. So what's your vote? Is she younger? Who thinks she's younger? The one that traveled. Okay, who thinks the one that stayed at home is going to be younger? Okay, nobody thinks that. Why? Why do you think the one that stayed at home isn't going to be the one that's younger? There seems to be a gut reaction that you guys have. That
Seems like she just stayed.
she just stayed put?
the same, yeah.
Like if we were a third distant bystander? Well, good. You're right. When they get back together, it's the one that traveled will be younger. And they'll both agree. You'll be physically older and you'll be physically younger. Well, you don't go back in time. You can't travel back in time. But she might have aged 4 years where you aged 50, depending on how long and fast. Go ahead.
My question was, I can understand how when they're in the same position, when their relative positions it's not different, they can agree on it, but how would someone in space think that someone on Earth is aging younger? I mean, I can understand how...
How would someone in space think someone at home's aging younger?
Yeah.
Easy. You're in the moving reference frame, right? But you're in that reference frame. Let's say you got no windows or anything. So if there's nothing around you, relative to you in your reference frame, what does it look like she on Earth is doing? If you head out away from Earth and near the speed of light, and you just look back through the window, what do you observe about Earth? What's it look like Earth is doing? Help him out. Yeah. It looks like it's staying, not just like it's staying put, it gets smaller and smaller and smaller. So from your reference frame, and remember, no reference frame is preferred. There's no absolute reference frame. So if you got nothing else as an indicator, it could easily look like the Earth is all of a sudden just took off and went that way, away from you. The point is, you observe motion, relative motion between you two, right? You're not moving relative to your spaceship, but Earth is. It's getting farther and farther away from you, period. No matter which one's really moving, it's moving away from you. So there's relative motion between you. Thus, you observe time dilation and length contraction for that reference frame, just because there's relative motion between you. And vice versa. It just seems more obvious this way because we said the rocket ship's moving that way. Well, that makes sense. But if you're in the rocket ship, the Earth's moving away from you also. Hence the paradox. Who's right? So the only real difference here is it's at the end. And that's where we had to employ general relativity. We're not going there. But the gist is special relativity works in uniformly moving reference frames. So when you're moving at a constant speed away from Earth and coming back. But what does she have to do to turn around? Decelerate, stop, turn around, accelerate, and change reference frames. So she was actually in 2 different reference frames, moving around, where the twin that stays at home is only in 1 reference frame. And that one's different than these 2. So she was changing reference frames. Ultimately, that's why she's the one that's younger when they get back together and they agree. Yeah?
I was going to ask a question about the contraction, but I don't know if I should ask it now.
Go ahead.
Well, like with the fish, I read in the book that it says this contraction is real. It happens. It's not just perception.
Right. It's
So
not.
I was wondering, like if the spaceship was a giant, like empty Diet Coke can, and it contracted, when it got back, would it still be contracted?
Good question.
Wouldn't the guy say, "Well, it looks like you're kind of crumpled up there"? I mean,
Good question. So, let's use this. She's got a Coke can on her in the ship, right? As she's moving away, what do we observe about the Coke can? Us here at home?
it's getting smaller.
Yeah, it gets smaller. But so does the contents within it, the space around it, the spaceship, and everything. Nothing seems funny to her because she's at rest with it. But to us, it looks smaller. And when she's coming back, it looks smaller, right? But when she stops, she's not moving anymore with respect to you. You're both in the same reference frame. There's no relative motion between you now anymore. So there's no more disparity. There's no more length contraction. The can looks normal. There's no more time dilation.
So isn't that a perception and not a...
No, because she's still physically younger. Because she aged more slowly while she was traveling. Like her heartbeat to us. We're at rest, and her heartbeat, instead of being boom, 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 we might have seen it as boom, 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 boom. But when she gets back and we're in the same reference frame, what do we observe now? Boom, 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 because there's no relative motion. So she now ages at the same rate as we do. But that whole time she was traveling, she aged more slowly. So by the time she gets back, she's younger than we are. Because she didn't age as much as we did. But once you're at rest, everything's back to normal rate. There's no more time dilation from that point on.
I have 2 questions. So, if somebody's heartbeat did slow down that much, wouldn't they die in space?
Would they die? Yeah. We wonder, we see them and like, whoa, how are they surviving? Okay, think about them, right?
I mean, from their relative position.
Yeah, to them though, I'm fine. My heart's normal. So they live just fine. So yeah, they don't die.
That's what I'm having trouble wrapping my head around, is that it's not the perceived heartbeat.
Yeah, it's like you never see this about yourself. None of these changes are like for you. It's always seems to be the other guy. And so everything's fine to you. You can survive just fine. I know. Go ahead.
So when you get back, since there's no disparity anymore, I'm still not wrapping my head around why the person in space would be younger, like why they would be physically younger.
Why are they physically younger?
When they were away the same period of time.
All right, let's do this animation then. That's what I'm going to do. We'll see if this helps explain it.
Nothing, yeah. I would like to see you. I must relax and I can't relax. I'm too old to relax. Look at the size of this one, would you?
Could a situation like this be true? You bet it can. This is time dilation. We can see time dilation by comparing clocks from different frames of reference, say from the Earth and from a high-speed rocket ship. Now, a clock can be anything that measures periodic intervals of time. To simplify, we're going to let the ticks of our clock be periodic flashes of light. Look at the light flashes emitted by the stationary rocket ship. Now, some time goes by before they reach the distant planet, but since there's no relative motion involved, successive flashes get to the planet at regularly spaced intervals. That's to say, both the sender and the receiver will agree on the time intervals between the flashes. Now, there's nothing unusual about this. But suppose the rocket ship moves. Look at the Doppler effect. An observer sees the flashes at shorter intervals. Suppose the ship moves fast enough so an observer sees the flashes at intervals twice as short as the ship sends them. Then if the ship moves away just as fast now, an observer is going to see intervals twice as long. Like if the rocket sends a flash every 6 minutes, they'll be seen every 12 minutes by the observer when the rocket moves away.
To your left, when they pass a station here on the left, they see it happening more frequently. They receive those wave fronts at a faster rate. Whereas if you're behind the rocket, you see them spaced out. That part makes sense? Okay, question in the back?
So if so time slows down a little when you're traveling away, when you're traveling back, the time speeding up cancels the...
Yeah, so time slows down going away, but coming back. Wouldn't the effects just cancel? We'll see. Oh, but after this question.
Would the first hit that reaches Earth be 6 minutes up?
Yes, as it's... Well, first it moves away from the Earth.
Right, that's what I meant.
And so Earth, over here on the right, gets those signals 12 minutes apart.
With the first one, would it be 6?
No. Say the rocket's right there. And let's say it emits one right then. It's like the starting gun, if you will. Okay. They're simultaneous there because they're together. 6 minutes later, according to the ship, he emits a second signal, right? But he's in motion now. So that wave leaves the ship and gets to the Earth. But it'll take 12 minutes because he's moving away. And so then the first one will be 12. So as the ship's moving away, the Earth receives them every 12 minutes, even though the ship's sending it every 6 minutes. And then vice versa when coming back. The ship's still sending it 6 minutes, but they bunch up in the front, so the Earth now receives them every 3 minutes. Does that effect cancel? Let's see.
But every 3 minutes when the rocket's approaching. Now let's apply this to time dilation. If the ship passes by the Earth and moves away at the same high speed for 1 hour and quickly turns around and then returns in 1 hour, rocket ship time, this 2-hour trip is seen by the Earth as taking place not in 2 hours, but in 2.5 hours.
What seems to take 2 hours on the rocket ship seems to take 2.5 hours for those on Earth.
And this is because the ship and the Earth have been in completely different realms of time. Let's look at this in greater detail. Suppose that when the ship goes by the Earth, that clocks on Earth and on the ship are synchronized to 12 noon. Then as the rocket leaves the Earth, a flash of light is emitted by the ship every 6 minutes. That's 6 minutes rocket time. Then the ship emits 10 of these 6-minute flashes while going away from the Earth.
Flashes. The ship. Because in an hour, that's 60 minutes. 60 divided by 6 flashes, or 10 flashes is every 6 minutes, or 60 minutes. You with me? So the ship emits 10 on his way out.
The 10th flash is going to be emitted 60 minutes after leaving the Earth. Then the ship's clock is going to read 1 o'clock just when this 10th flash is emitted. Now suppose this is the moment that the ship turns around. Our Earth observers don't see the turnaround until they see the 10th flash. Now here it comes. It's going to take some time for it to get to them. Closer, closer, closer.
See in the bottom left-hand corner it says 15? That's how many flashes the Earth has detected thus far.
Bam, there it is.
At intervals of 12 minutes. Right? So 16 times 12, they'll do the math for you in a second.
10 flashes, 12 minutes apart. That's 120
Oh.
minutes.
That was the 10th flash it detected. I'm sorry. That was the 10th flash it detected. The ship has emitted 16 at this point. Sorry.
2 hours. So that means it's 2 o'clock now on Earth.
Well, you can get it there. If the ship emitted 10, and the Earth detects those every 12 minutes apart, 12 times 10 is 120 minutes. That's 2 hours. The Earth has seen 2 hours pass. But the ship's not back yet. So you can see already the times are going to disagree.
Now the 10 flashes the ship emits when approaching the Earth, they're going to be seen 3 minutes apart, or all 10 in 30 minutes. The first is 3 minutes after 2 o'clock, Earth time. The next is 3 minutes later. The next is 3 minutes later, and so on, until the last flash is emitted just as the ship whizzes past the Earth. And that's going to be 2:30, Earth time. So a clock aboard the rocket ship reads 2 o'clock, while a clock on the Earth reads 2:30. This checks out. Check the figures.
They disagree. When they get back together, the person that was on the ship seems younger. So they don't exactly cancel. Freaky, huh? Now, how many of you are Ender's Games fans? Who's read the book? Who's seen the movie? Oh, I thought it'd be more of you. I forgot to pull it up. Let me grab it here. Miscellaneous. There's a passage in there. I've only seen the movie. I won't lie. I got this from my wife. So it's chapter 14, Ender's teacher. What's his name? You fans? Remember Ender's teacher's name at the end? Oh, well. So the gist is, there's a big battle. These aliens are conquering Earth, and this one guy was successful and beat him once. Who becomes his teacher. Well, they realize, oh, we need to save your knowledge. You're the only one who knows how to beat him. So we got to keep you alive to teach the next bright pupil. And that's where Ender comes in. And so ultimately they get together, and the master teacher is teaching Ender everything he needs to know. Well, Ender finally realizes, I'm not ruining the plot line here. Too much. He asks him, wait a minute, that happened a long time ago. Why aren't you dead? At the top, why aren't you dead? Ender asked him. I'm right up here. He said, you fought your battle 70 years ago. I don't think you're even 60 years old. And this is great. Orson Scott Card used special relativity. So next paragraph. The miracles of relativity, said Maser, that's the master teacher. They kept me here for 20 years after the battle, even though I begged them to let me command one of their starships they launched against the bugger home planet, that's the aliens, and the bugger colonies. Then they came to understand some things about the way soldiers behave in the stress of battle. What things? Blah, blah, blah. Then right here. So they sent you out in a starship and you got up to relativistic speed. This is good physics. And then I turned around and came home. A very dull voyage, Ender. 50 years in space. Officially, only 8 years passed for me. It felt like 100, 500, but also I could teach you everything I wanted to know, you needed to know. So when he got back, he realized 50 years had passed on Earth. But it only seemed like 8 years to him. We know what happened. There was relativistic motion between the reference frames. And what that factor, 50 divided by 8, I figured it out, because I'm a geek. You guys can do this too. 50 divided by 8 is 6.25. That's the Lorentz factor. If you plug that into what the formula is, that means he was going, I did it here at the bottom, 98.7% the speed of light for 8 years. He went that, stopped, turned around, came back. Gone for 8 years. 4 years that way, 4 years back. At that speed, would have this effect. The Earth would seem to have passed 50 years, while only 8 passed for you. So what's cool about this, not only did we, maybe I shouldn't spoil it, but it ends happy. Space travel. Maybe it's possible now. Once we can work out this momentum infinite increase as you go faster and faster, and it takes more and more and more and more energy to go faster and faster, there's a problem. And radiation killing you. But that aside, let's see, the closest thing to us, Alpha Centauri is 4 light years away. That means it takes light 4 years to get there. So if you could travel at the speed of light, it would take you 4 years to get there. Say you traveled there, played around a little, and came back. That would take 8 years of your life. We would think that astronaut was gone for 8 years. No. So would the astronaut would think it took 8 years. 4 years to get there, 4 years back. Well, what if you traveled at 87% the speed of light? What's the Lorentz factor? Anybody remember? 87%. Yeah, the Lorentz factor is 2. So for you, it would seem like it only takes 2 years to get there. 2 years there, 2 years back. So 4 years passed for you. 8 years would pass on Earth. That's your sacrifice. The center of the Milky Way galaxy is 25,000 light years away. People think there's no way we could get there in a lifetime because nobody lives 25,000 years, right? Well, sure. So we sent an astronaut off at 87% the speed of light. Well, they wouldn't make it still. You'd have to go like 99.999995% the speed of light. The Lorentz factor is 1,000 then. How long would it take? 25 years. So for you, it would seem to be 25 years there, 25 back. So you could do it. 50 years of your life to go see the center of the Milky Way galaxy. How many years just passed on Earth, though? When you get back, Earth might not even exist. 50,000 years have passed. And you can't go back in the past. That's your sacrifice. To end up back in the same spot in space, you have to give up some time if you want to come back. You can't travel in the past. It's only forward. But at least now you could do it and get that knowledge. You just have nothing to come back to, maybe. That's space travel with this space-time.
Does that all affect the clocks on Earth, that is smaller amounts that we don't really have?
Does it affect? Well, the clocks on Earth that are at rest relative to Earth?
Well, I mean, clocks that are accelerating.
Yeah, so they tested this out in 1971. They took some really sensitive cesium atom clocks on high-speed airplanes. And they whizzed around the Earth. One went one way, one went the other way. And they did this twice. And the upshot was they're moving at higher speeds. Not super fast, but for us, fast. And sure enough, when the clock that was going really fast, and they brought them back together, one was at rest on Earth, sorry. They did the plane, they made it go both ways to test. So one was moving, one was at rest. And when they brought them back together, which clock, were they the same? No. The one that was moving relative to us at rest was physically slower. It was behind. A minuscule amount for us, but it was noticeable for the sensitive clock.
It doesn't have any practical.
Only if we can start doing space travel. when things start becoming more relativistic speeds for us, then it'll rear its head. But we never notice it because we're always going slow. But when we start using technology where those things are going fast, again, like satellites or subatomic particles, we have to account for it or things don't make sense. The Large Hadron Collider where they're smashing things in, maybe you've heard of the Higgs boson. Well, they are fast, relativistic. We do have to think about it. But for us in normal day life, no. But it's fun to imagine and think about this stuff, and we will have to worry about it someday eventually.
I have a question about volume.
That homework question? Yeah. The idea with volume is a length contracts. So does your volume. Your volume is going to change. If the length contracts, your volume shrinks. But only in the direction of travel, the length. But that means there's less volume. Well, that was good though. I thought we'd have a little more time here. I'll skip. I had a couple clicker questions for relativity. I think we discussed it. Let's review in the last 5 so minutes the other stuff. Volunteer. Who trusts the conservation of energy law? You believe it? Okay, will you be my volunteer? Got to trust physics. Come over here. And I'm going to ask you to stand here, hold it like this, right up against your eyeball, like this. What we're going to have you do is let go, whoosh, and you have to hold still. Because the ball will swing back, right?
Yeah.
Will it hit you?
Should.
You think it'll hit you?
Well, it won't because we have all that air resistance.
What kind of energy do we have at this point? Gravitational potential. So relative to, don't let go. Relative to here, we've raised it up. We did work, right? You had to exert a force over a distance, right? We raised it up. Well, that changed its energy, so now it has gravitational potential energy. When he lets go of it, where's that energy going to go? Because it lowers. Kinetic. And where's it at maximum? Right at the bottom. It just changes forms. And then it comes back into what? Potential. No kinetic. How about right here? Both. Right, okay. So right up there, up against your eyeball. Don't move. Let go of it when you're ready. And let's see what happens. Good job. Everybody does it. It's like you trust physics, but you don't want to be stupid, right? Just play it safe. But yeah, total energy is conserved. So what's the only way this ball could come any higher than it started?
If there's additional forces out.
Yeah, if you push it, additional force adds to it. That's why I have people do this. If they accidentally go like this, sometimes people push it. Because then you know what's going to happen.
Has there ever been any disaster?
And then then you better move. Only one little kid who wasn't paying attention, and he moved. And it came and went like this. And just kind of nicked him. But then he was scared and embarrassed and started crying. It didn't hurt him, but it wasn't a fun moment. So, let's see. The hard part's holding still. Now, it doesn't come up as high even though as I let go. Why? It should. Total energy is conserved, right? Air resistance and friction up there. So it's both turned into heat. So if you account for that energy, the total is conserved. But it's not in our system anymore. So it's left the ball. So the ball can't get back its full potential energy again. And you can see it gets lower and lower eventually. But there's your good review, right? I like that one. Let's do this one. All right, 2 balls, 2 ramps. I call it the high road and the low road. I'm going to let go of them at the same time, at the same height. They're going to roll down, but they take different paths. Who will win? Or will it be a tie? I should have made this a clicker question. But for lack of time, what do you think? Tie? Who thinks a tie? All right. Who thinks the high road will win? Who thinks the low road will win? No takers. Okay. Drum roll, please. Low road. You're like, dang it. But I do this because it reviews a lot of things. Try to solidify this. Okay, there's a fair amount of ties. Why'd you think that?
Well, I thought what was going to happen is that it would accelerate when it was going downward.
Accelerate here, which it did. Good.
And it would encounter too much resistance going back up that would end up slowing it down.
So it decelerates to come back up. And both of that's true. However, it's still 1. So you're right. It accelerates here. You guys see why, right? And it decelerates here. Excellent. But that wasn't enough to explain it. So why did somebody think the high road would win? Or go ahead.
I was going to say why I thought the low road won because it gained more energy as it went down.
Oh, it gains more energy. Okay. Right here, how do their energies compare?
They're the same.
And in what form? Potential and kinetic because they're moving. But they're equal. So they have the same total energy. At this point, how do they compare? The lower has more kinetic because it's moving faster, which means it has less potential. Well, it's lower. It better too because how do the total energies compare? They have to be the same. We started out with the same. It didn't magically appear or disappear. It's just more of its kinetic now and less potential. But it's going faster, right? It's got more kinetic energy. It's accelerated. So during this stretch, who's going faster? The lower one. So it gets ahead, doesn't it? All right. Now we get back to here. Or something like this. Okay, it slows back down. You think it has time to catch up. Well, what's the energy do? What's the low road do on its way up, energy-wise? Gains potential, which means it has to decrease kinetic. And they're back to symmetric. They're going to go the same speed when they're in this section. Do you see that? But who's going faster at this moment? The bottom one. He hasn't slowed back down to this speed yet, right? So he's still moving faster in this range than this one. So he still gets ahead, just not as much as it did here. Let's watch it again. Total same energy. Speeds up, picks up, still moving faster there, so he wins. If I stagger him, I can try to get him to match up, to hit this spot at the same time. Let's see. Which one do I have to let go of first? The high road. Here we go. I'll try it again. It's pretty close. When they're here, compare their speeds. They might not be in sync because I'm not excellent, but their speeds. They're pretty much the same, if I leveled this well enough. And they have to be. They're back to the same potential, so they have the same kinetic. They should better be moving the same speed. There, does that kind of help this interplay? All right, one more. Because we did collisions. This is one of my favorites. I'm going to drop a basketball and a tennis ball like this. And we're going to collide with the floor. There's going to be an impulse, right? What's an impulse? Force times time. There's going to be a force applied for a certain amount of time, which will change its momentum. Excellent. The two ways to think of it. An impulse is a change in momentum caused by a force. So that's the floor exerting a force on the ball. Well, then these two are going to collide. What has to stay constant, conserved in this collision? Energy and momentum. Which one's bigger? Yeah, more mass. So Newton's second law, who's going to be affected more? So let's bounce them both straight here and see what happens. Notice they don't come back up as high. Some energy is converted to heat. But let's see how high this one comes back up. About here. About here. Okay, now let's do it with the ball. We can get the ball to bounce a lot higher because this guy transfers some of his momentum to him. But if he transfers some of his momentum to him, what happens to his momentum? It has to go down. So watch where this bounces again. Here's normal. About there. Now watch this ball, not the tennis ball. A lot lower because some of his energy and momentum has been transferred to the tennis ball. But the total's still the same. They make a toy that does this, and it's like does it threefold. And this little ball gets all of it, but it's a lot smaller. So help me watch where this goes. You ready? Supersonic. But the idea is each of those, it's collisions, but because momentum and kinetic energy are conserved, the total, the little guy is the one that's moving, and he gets a lot more than he would by himself. What else did we do? You got any major questions? I know I didn't review everything. We had projectile motion in there too. Remember, horizontal and vertical are independent of each other. One can be constant while the other is not. Yeah.
I think a question on the homework was about hang time, and it said if you jump 4 meters or 4 feet horizontally, you'd have the same hang time as you just jump vertically.
Yeah, that's like, say you jump up vertically like this. If you go 2 meters up, that takes a certain amount of time, right? Up, down. It's based on the vertical G. Well, what if you go 2 meters up, but at the same time you go over? How long does it take to go up and down? The same, because vertically it went the same height. If this goes to the same height, vertically it has to take the same amount of time. It's just during that time interval, it also had horizontal velocity, so it moved down range.
So why does in the book it says if you have a running jump that you go horizontally, that would take longer time? Is that because they said like the action force of hitting the floor?
Right, I don't remember that. So if you're running...
So like a running jump will take longer than just...
A running jump will take longer than just jumping straight up in the air?
Moving horizontally, but...
While she's looking that up, remember our shooting at different angles? Maybe they land at the same spot if they add up to what? 90. But one might spend more time in the air because the up's greater than the sideways. This one would spend less time in the air. Page 178 for those of you who want to, and we'll end with this. If you want to hear the answer, stick around. If not, I'll answer her. So what happens over the action of running? Oh, the hang time for a running jump can exceed hang time for a standing jump. Okay, because generally standing, you exert a force off the ground. But that force is straight up. Well, if you're running, you can push, but that push is at an angle. And you can, when you're running, you can push harder for one, so that changes the force. And you add the components. Instead of just having the up force, you now, maybe I can only do this jumping straight. But if I'm running, I can do this and this.
So what do they mean?
So what's the resultant? I got an up of this and this diagonal, and that's a lot longer, a bigger force than just this. So that can keep me in the air longer.
Are we supposed to assume in the homework that you weren't running, you just jumped horizontally?
And maybe I'll look at that, because if I need to clarify, that's confusing. And yeah, it could be. Okay. I don't remember the exact wording of that one at the moment. But yeah, if it needs clarified, I can adjust points, absolutely.
I got it, but I got the answer.
No, yeah. Good observation.